So you're stuck real bad, but don't be sad. Mark is here to help you escape from Alex. There's gonna be some yummy pie filling.
Well, hi, everybody. Hi, Mike here. Today, we're going to do a rather multi-layered and complex problem in general chemistry 2 kinetics. We are going to solve for the rate constant and determine the order of something that we don't know the order of because they didn't tell us. Is it first, second, zero order? We don't know. They never told us. And so let me go ahead and share my screen with you so we can talk about what this is. This is a little topic here, right? Where are we going to go and find the rate constant, right? Down here. They want to know what the rate constant is. Boom. They want to know what the rate law is. And they didn't tell us what order it is. That's fine, because what we need to do is figure out, like, okay, what's the rate law based on looking at it here? And you can't. Well, actually, you can. You can rule out one thing. You can rule out zero order. What is zero order? Let's write that out, actually. What's zero order? Rate. And by the way, we'll save a lot of time if we just call phosphoric acid here. Can we just call that A, like we've been doing, capital letter A, like as if the reaction is just, A goes to make B, whatever the reactant is. So if that's the case, what's zero order mean? That means rate equals K times the concentration of the reactant to the zero power, which boils down to anything times the zero power is rate equals K. That means the rate is a constant. That means that the number of moles per liter change per time is constant, which means this is a straight line, right? This is Y equals X, something like that. So what you're going to find is that this is not the case here, gang, because here we go. Look at, 0.8 to 0.405. And then an interval of 0.4 there, an interval of 0.2 here, an interval of 0.1-ish here. It's looking like this particular thing is certainly not zero order. This is not a straight line. This is a curve. Let's get rid of that. This is not what the rate law is. It's going to be either an order of 1 or 2. Now, how are we going to find that out? There's 2 ways we can do it. It depends on which way you want to do it. There's a way that you can do that definitely will be foolproof. Both of them are foolproof, actually. But, there's one that takes a little more time, but it's easier to understand. And that is, we need to write out the equations for the rate laws of each order. So let's go ahead and just say, okay, first order. What's the relationship between the concentration and time? And it goes like this. It is natural log of the concentration of the reactant divided by the initial concentration of the reactant, which we will put as A subscript 0, equals minus K times time. Let's keep that on the back burner. That is the equation which governs these points if it's first order. What if it's not first order? That's certainly a possibility. Actually, I looked at the data. I think it's first order, but I'll tell you why in just a little bit. If it's second order, it goes a little something like this. Hit it. It goes 1 over concentration of A minus 1 over the concentration of A initial. Now, by the way, you don't have to think too deeply. You don't have to understand why these are the equations, unless you're a calculus freak. Then you can worry about that. But just, due to the powers of math, this is what the equation is for second order reactions, K times T. Let's put a nice little tidy circle. Let's make it even in a different color so we can differentiate from it. Let's make that over here. I guess so much for the other color. I got goofed up. Now, here's what we can do. If the rate constant is truly a constant, we can plug points in and see what the value of K is and find out which of these two equations is the equation governing the points. If I plug in T equals 0 and 10, so T equals 10 seconds, and the initial concentration of 0.8 and the 10-second value of 0.405, I'll get a K no matter which equation I use. But then if I do it again for 20 seconds, I'll do it again for 20 seconds T and 0.205 concentration of A and the same concentration of A initial of 0.8. And then I will get another K and it's going to be the same thing, meaning it's constant, or it's going to be not. So one of these is going to be the truth and one isn't. Now, let me tell you what, I'm going to tip my hand here, gang. I think this is first order, and let me tell you why. First order equations have a constant half-life. So what's the half-life of this? I don't know. It went from 0.8 to 0.405. That's not perfectly half, but almost at 10 seconds. That means that the half-life there is about a little bit more than 10 seconds. And then when it went from 0.405 to 0.205, that's about another 10 seconds. 0.205 to 0.104, that's about another 10 seconds. This thing has a half-life that looks pretty constant at about 10 seconds, a little bit less than 10 seconds. I think it's first order. Once you do a gazillion of these, you'll recognize that. You don't have to. You don't have to recognize that. You can forget the last minute of your life and just go ahead and do what I'm doing. What I'm going to do is I'm going to plug in numbers. I'm going to plug in numbers here using these 2 points for the first order equation. And then I'm going to do it again at time 10 seconds to begin with, and then time 20 seconds. And I'm going to see if I get a K that's about the same. If that's the case, I can put it in here. If that's the case, I can write the rate law, first order. Cool. Let's do that. Here we go. Boom. Let's write here natural log of, I don't like that color. I want to use something more authoritative, like black. Natural log of the concentration of A at 10 seconds, 0.405. Divided by, and I'm not going to put moles per liter in, it just cancels out anyway. Okay. So, and I know I'm a unit freak, but I'm not that much of a unit freak. 0.800, right? Equals minus K. We don't know what that value is yet, but we know that this is 10 seconds. Let's go crank some numbers. Okay. What's this going to boil down to if we just take the next step? Natural log of 0.405. 0.405 divided by 0.8 is 0.5. I forgot a little equal sign there, didn't I, gang? Boop. Okay. Sorry. Where was I? 0.405 divided by 0.800 equals the natural log. Boom. Negative minus 0.6807 2466 equals minus K times 10 seconds. Let's solve for K. Why don't we just go get rid of that silliness that is the negative sign on both sides. Cancel it out. Negative sign on both sides. This is going to be K is 0.06807. I quit after that. Inverse seconds. Those are the units of a first order rate constant. Keep that on the back burner. We've proven nothing yet. The way we prove something is we go and we do this again, except we do it with a different set of points. So let's go and take 0 and 20 seconds, do the same exact process. All right. So natural log of, and the initial concentration doesn't change, 0.205 moles per liter. I'm just saving time by not putting in moles per liter. Okay, gang. 0.800 equals minus K times T of 20 seconds. Let's take that another step out. What do we get? 0.205 divided by 0.8, and then take a natural log of it. 0.205 divided by 0.8. Natural log, negative 1.36. Let's just go to a number of reasonable digits. 1.6 equals negative K times 20 seconds, right? K equals whatever minus 1.36. Oh, darn, I had it. 1.36. 1.6 divided by 20.06808 inverse seconds. Now, gang, that seems like the same K constant to me. I even hit my calculator button wrong and didn't, take all the digits. That seems like this is first order. Now, I did say that it looks like it cuts itself in half-life in half at a regular interval because of the nice generosity of the numbers here. Now, let's prove that it's not second order by plugging into the second order equation and finding out that that is not the case. However, if we were in a hurry, we could write rate equals K, K times concentration of H3PO4. Don't do it like I'm doing it. Do it with the proper superscripts and subscripts here to the 1 power K, as we found out, 2 significant digits, 0.068, and they want the correct unit symbol, inverse seconds. That's my answer for now. I didn't put it in stone. It's just my answer for now. Okay. I'm just going to go ahead and be careful and disprove the other equation. And there's even a different way you could do this, but I'm not getting into that yet. Let's plug in these values. What did we do? Red the first time? Whoop. Let's plug that in. Let's get a K. All right. We're going to use this equation this time, gang. What does the second order equation do for us? And I don't know if your professor is going to make you commit these to memory. If that's the case, that's unfortunate, but hey, that's how it goes sometimes. This is in molarity units, inverse molarity units. I'm not doing it because I'm trying to save time. So divided by 0.405 equals, you know what? Actually, I'm going to put units in. I want to make a point. That's in molarity. Equals K times 10 seconds. Okay. Let's invert this. What's 0.8? 1 divided by 0.8 is 1.25. 1.25 inverse molarity units. It's concentration minus 1 over 0.405 minus 2. Doggone it, I screwed it up. That's okay. I screwed it up, but I'm gonna make it. I got the 2 different. And I'm going to show you how we can undo that. 2.469. Do you see how, and I've been, this has been a theme. Your buddy Mike goofs stuff up, but recognizes where I goofed it up. What did I do? I got, this is not the initial concentration. These two are backwards. But the difference will still be the same. If I took 2.469 minus 1.25, that would actually be the same sort of value, same thing, as if I, had it the other way around. So I'm not, it's actually a happy accident, as my favorite painter, Bob Ross, would say. So what I'm going to do is I'm going to take 1.25 minus 2.469, and I'm going to find out that that's negative, but still should be the same value, 1.219 inverse molarity units equals K times 10 seconds. Divide both sides by 10 seconds. And what do we get? K equals 0.1219. Now, let's think about what the units are. Inverse molarity divided by seconds. They might want more than that. It ain't the answer anyhow. Inverse molarity is moles per liter upside down, liters per mole per second. That is the units of a second order rate constant. All right, let's keep that. 0.1219 liters per mole per second. That's the 10-second value. Do it all over again, except right this time for the 20-second value. Do we get 0.1219? Boy, I hope not. You can't have two constant Ks for two different equations, all right? So just to make a little point here, I'm going to take that point again, that point again. I'm going to plug it in. This time I'm going to not goof up the order of it. 1 over concentration of A would be 1 over 0.205 molar minus 1 over 0.800 molar equals K times 20 seconds. Boom. Here we go. What's 0.205 inverse? 4.878. Inverse molarity units minus, well, we did it last time, it was it was 1.25. Inverse molarity units equals K times 20 seconds. Cool. Let's do this. 4.878 minus 1.25, 3.628. Inverse molarity units equals K times 20 seconds. Let's divide both sides by 20 seconds and see what we get for K. K is going to be 3.328 divided by 20. And it ain't going to be 0.129. As a matter of fact, it's much different. 0.18, which is way different than 0.12 something. 14. All right. Inverse molarity is liters per mole. So liters divided by moles per second. Seconds is lowercase. Fat finger in it here. So not the same value. Gang, this is not second order. We did not get the same rate constant from the second order equation. If you really, really, really wanted to produce this this feeling of, like confidence, you could go put in 30 seconds into the first order again, and you could find out you get the same K value. That is a first order equation. This is the right answer. If you give me 5 more minutes, I'm going to show you a different way to do it if you like. Okay. So that took a little longer. The way that takes less time and might be the subject of some more questions in different format is that if you look at this, let's make this a different color here. If I plug this y equals mx, y equals mx. If I were to plot the left side of the equal sign versus time, that has the form that could be linear. I could do this. I could say, hey, natural log of concentration of A divided by, concentration of A initial. I could put that on the y-axis, put T here. If I get a y equals mx form, negative slope line, that means that that's first order. What would the slope be? Slope would be equal to K. For you graphy kind of people out there, actually it'd be equal to negative K. Slope would be equal to negative K. If you were really wanted to be exacting, you could do the same thing here. What if you do 1 over concentration of A minus 1 over concentration of A initial? The slope would be positive K. So what we're going to do, though, is half of this stuff is constants. To get rid of the A, 0, A initial, we just plot natural log of concentration of A. We're going to do 1 over concentration of A. Why did I not put the initial in there? Remember, it was a constant. So 1 over concentration of A. And I'm going to monitor its progress and see what one has a regular interval and see which one's linear. That tells you which equation's producing the points. If you love graphs and spreadsheets and all that kind of stuff, this is not for everybody, but it is quicker. Watch how much quicker it is. 0.8, natural log, boom. Negative 0.223. Let's just quit there. 0.405. Natural log, boom. I don't have to do the boom every time, but I kind of like it. Negative 90387. Okay. 0.205. Natural log, negative 1.58. Let's just quit after that. Let's see what, 47. Let's monitor the interval. Is this a linear relationship? What was the difference here? What was the difference there? If it's the same, it's linear. I'm even going to ditch the negative signs because they're probably they are the bane of my existence. 0.90387 minus 0.223. That's a difference of negative 0.681-ish. Hold on. What's the difference here? 1.5847 minus 0.90387, 0.6808. That further proves that this equation is producing those points and not that one. Let's go and disprove, though. You know, you don't want to just prove, you want to disprove. Let's go and do 1 over A's. What's 1 over 0.8? Well, we did that. It's 1.25. What is 1 over 0.405? I forgot. 2.469. 1. What's 1 over 0.205? 4.878. What's the interval here? I'll write it in blue colored ink. No, it's red. Whatever. Fine. I want it to be blue. There. Because I want it to be wrong. 2.4691 minus 1.25. That difference is positive 1.219. What's the difference here? Well, I can tell already it's over 2, right? 4.878 minus 2.4691 is a difference of 2.4 something. I'm done with second order. I've been doubly proved that it is not the equation producing these points. Why? 3 different ways I proved this. Not proved. The first time I had an instinct, an intuition that, you know, hey, it looks like the half-life is something like a little bit less than 10 seconds, and then a little bit, almost a little bit more than another 10 seconds. Looks like it cuts itself in intervals, you know, after a little bit less than 10 seconds, regular intervals, which is what a first order equation does. Secondly, I plugged it into the first order equation, this thing right here, where I said, hey, let's plug it in and calculate K. I got the same K every time for both 10 seconds and 20 seconds. I could have gone and done 30, 40 seconds. Secondly, I plugged it into this equation, found out that that didn't give me the same K. Thirdly, I did the graphical method where I took the variable part of the integrated rate law, which I hope you don't have to commit to memory, but if you do, throw it on a flashcard. When you're walking to class, memorize them, throw them in short-term memory. It won't be there when you're old and taking care of your grandkids. It'll just be something you have to endure right now. But when you do, you know, you go and say, okay, the variable part, natural log of A, if I plot that versus time, this one is linear, which fits the linear format of plotting this versus K and T. You get a positive K, I mean, a constant K. When I did it with this, I didn't get anything near constant. That means that this is a first order equation. If we did the opposite and the second order equation gave you the same K and 1 over A was, you know, the same linear relationship, it would have been second order. And now that's really everything we've done has gotten us to the point of which equation do we use? And do we use the equation? Nope, we just solve for K, because otherwise this thing would take so long that it would make you want to go and stick your head in the freezer for half an hour straight. So that is my presentation of deducing a rate law from the change in concentration over time. I hope I did you good on this one. If you got enough time on the test to do it, great. But I don't know if this is going on the exam, guys. I mean, it's like they'll probably say, hey, what does this mean? And you'll be like, oh, that means first order, multiple choice format. Here in Alex, find yourself in a happy place. Go get your munchie on, go get your sleep on, come back to this because you're going to have to do this 3 times in a row. Do we do another one? Could be second order the next time, could be whatever, but you're going to have to choose one of the 2 methods I've shown you here to do this 3 times in a row, unless it's part of a knowledge check, which, oh my goodness, would that be terrible too. So once you get over this hump, activation energy, you've gotten over basically the hardest part of kinetics. And I wish you congratulations on getting to this point. So, got a problem? Drop it in the comments. See you in the next one. And ciao for now. Peace out and vanadium too. Bye.